In this video, we're going to look at how we use matrices to define our linear transforms and basically have a one-to-one mapping between those two things. In the very common case where we're looking at transforms between various real dimension spaces, Rn to Rm, we can capture everything about the transform with a matrix of the appropriate size. We'll talk about that in a second. Once we have that matrix form, we're going to be able to answer more easily a lot of the questions we've already faced and kind of done on an ad hoc basis. We're going to be able to find the dimension of the kernel of L and find a basis for that kernel. Remember, the kernel is all about which space? Ask yourself for a second. Right, it's about the inputs that map things to 0. And then the image, we're going to be able to do the same thing. We're going to be able to talk about the dimension of the image and a basis for the image. And again, that will be properties of the output space. What parts of the output space does L let us reach? Now, one of the fundamental ingredients for these matrices related to linear transforms is simply going to be their size. And anyone going on to any computing later on, dealing with size of matrices is going to be something you'll have to struggle with, deal with going forward. Just to recall, when we talk about matrices, we have a standard order for describing them. It's always rows by columns. So if we're looking at this matrix here, this is a 2-row by 3-column matrix. This one here is a 3-row by 3-column matrix. And so we'd express this typically as a 3 by 3 matrix, and this is a 2 by 3 matrix. There's not much we can say about that besides this is how the nomenclature works. Now, what's more of a fun fact is if we take a look at all the matrices of a given size. So going back for a moment, imagine not just this matrix, but any matrix that has this shape of 3 elements and 3 elements underneath it. You know, -10, 14.7, all that, any random numbers, but in that same layout, that set of matrices defines its own vector space. So we could have the vector space of 2 by 3 matrices. In fact, we do. That is by itself a vector subspace. You can imagine the building blocks of it. If we go back for a moment, if I put a 1 and then 0 everywhere else and a 1 here and then a 0 everywhere else, I could make any matrix of this shape with those 6 building block matrices and through using linear combination. So all that good stuff is there. We do that based on addition just being element by element. We would define that multiplication operator as just multiplying every element of the matrix. So if we do that, we can linearly combine matrices of a specific size with each other as much as we want, using these addition and scalar multiplication operators. So for example, if we take a 2 by 3 matrix, 1, 0, 2, 0, 1, 5, it makes total sense under this kind of logic to add it to some other matrix. Just to keep it simple, have mostly zeros in there. But we can go element by element. So 1 plus 2 is 3, and 0 minus 1 is -1, 2 plus that is 2, 0, 1, 5. We simply took each element in the corresponding matrix, added it to get the new element in the new matrix. Of course, that's fine, but if we tried to imagine adding a 2 by 2 matrix to a 3 rows by 1 matrix, then that's not well defined. There might be a way to define it, but it's certainly not a natural definition like this one here that we applied for these 2 by 3 matrices. So again, just a nice sideline. It's not particularly central to the course that these are vector spaces, but given that's the language we're using, it makes sense to identify it when it pops up.